Now, let's have part 2 of our module on calorimetry. This second module is most likely to attend to our intended learning outcome, which is to relate the heat of the reaction and the amount of the substance. After knowing how heat is computed through Q is equal to mc delta T and how heat is measured, we now discuss the heat of reaction delta Rxn. Okay. For this topic, it is important for you to think that when there is a chemical reaction, it is always gonna be accompanied by heat absorption or heat rejection. For us to know the amount of heat that is rejected or absorbed in chemical reaction, we consider the amount of heat present in the reactants and in the product. Okay. Thus, we have this pattern mathematically that the delta Rxn is equal to the enthalpy final minus the enthalpy initial, or the enthalpies of the products minus the enthalpies of your reactants. Okay. So again, our thinking is either heat is absorbed or heat is rejected. So what happens when heat is absorbed? When heat is absorbed, this delta or difference in the enthalpy should be positive, and again, that implies an endothermic process. Now, when heat is released, this delta Rxn is gonna be negative, and again, we will have an exothermic process. Okay, there will also be times that this difference or the amount of heat that is absorbed or rejected is given in our equations, okay, such as this one or these two that are given to us. Okay, first we have our reactants as our reactants A and B, and our product are actually C and D. Now, for this first reaction, we have the heat term to be included in the chemical reaction, okay, as part of the reactant. Now, another reaction that we have here is that we are still having A and B as reactant and C and D as our product, and the heat term now is actually on the product side. Okay, these are actually called as our thermochemical equations. Now, again, to note that heat is absorbed, okay, we will be having the heat term on the left side of the equation or in the reactant side. Now, when heat is released, then expect the heat value to be on the product side of your thermochemical equations. We now have stoichiometry of thermochemical equations. Okay, remember stoichiometry? Okay, so we will still be having that since we will be dealing with chemical equations, specifically thermochemical equations. And for us to be able to use those thermochemical equations, we have the following guides. First of the guides is this. The delta H for a reaction is equal in magnitude but opposite in sign to the delta H for the reverse reaction. Okay. So to show this, let's say we have this reaction of water decomposing to its hydrogen and oxygen components. Okay, having a endothermic reaction of 572 kilojoules of energy. Now, when we reverse the equation such that our hydrogen and oxygen becomes our reactant, okay, our heat of reaction will be having the same magnitude, only that this time, this is going to be having a negative value. Okay, so we highlight this in this box, values. Now, the second guideline is to note that enthalpy is an extensive property, meaning it depends on the amount. So the magnitude of delta H is directly proportional to the amount of reactant consumed in the process. Okay, thus if we have this equation that when 1 mole of hydrogen adds with 1/2 mole of oxygen and it forms 1 mole of water and involving a negative 286 kilojoules of energy as heat of reaction, okay, then this value of energy will be stoichiometrically related to the amount of our reactant and product, okay, meaning that 286 kilojoules is thermodynamically equivalent to 1 mole of H2. Okay, so that 1 mole is simply the coefficient of H2 in our thermochemical equation, and also thermochemically equivalent to 1/2 mole of O2, okay, as given in the thermochemical equation, and 1 mole of liquid water. Now we have the third guideline, and it says that the delta H for a reaction depends on the state of the reactants and products. Okay, for this third guideline, we have water as an example. So note that water can actually melt. So from solid water to liquid water, it can actually utilize 6.01 kilojoules of energy. Now, it is important for you to take note that when we convert liquid water to gaseous water, we normally would be utilizing greater amount of energy, which is actually supported to us by the 44.0 kilojoules of energy used here. Now we proceed to example 7 of the module on thermochemistry. And the problem says that the decomposition of aluminum oxide can be expressed by this given equation, that 1 mole of aluminum oxide, once heated, will be producing 2 moles of solid aluminum and 1.5 moles of oxygen gas and a delta Rxn of 1,676 kilojoules. Now, if aluminum is produced this way, how many grams of aluminum can be formed when 1.000 times 10 to the 3 kilojoules of heat is transferred? From the problem, we have this equation, again, of the decomposition of aluminum, and we are asked to solve for the grams of aluminum formed when 1,000 kilojoules of heat is transferred. Okay. As a start, we concentrate on the energy value that is given to us. Okay, so we are to do conversion of the heat to the number of moles of aluminum, okay, using the relationship that for every 1,676 kilojoules of energy, it actually utilizes 2 moles of aluminum. And then from then, since we are asked to solve for the mass of aluminum, we will be utilizing the molar mass of aluminum, which we can obtain from the periodic table. Okay. Now, how do we compute for that one? So again, we start with a given amount of 1,000 kilojoules of heat, okay, and then we use the relationship as what we have highlighted here, okay, as that for every 2 moles of aluminum, it actually utilizes 1,676 kilojoules of energy. And then, from the periodic table, we obtain the 26.98 grams per mole molar mass of aluminum. Okay, so doing the computation will actually allow us to obtain the needed mass of aluminum, which is 32.2 grams. Now, moving forward, we have HESS'S law of heat summation. Okay, according to the law, the enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. Okay. To illustrate the overall process and individual steps, let us consider this system for the conversion of carbon to carbon dioxide. Okay. On this illustration, we have the overall process such that from graphite, okay, it reacts with oxygen to form directly carbon dioxide, and it utilizes 393.5 kilojoules of energy. Okay, now the individual steps that is pertained to by the law is this. Okay, now remember that carbon can actually undergo incomplete combustion with oxygen. Okay, so if that happens, so carbon, when it reacts with oxygen, okay, would only be obtaining muna carbon monoxide. Okay, and if that happens, it will be utilizing lesser energy at negative 110.5 kilojoules. Now, further heating of our carbon monoxide, of course, will lead us to the creation of our product, which is carbon dioxide. And for this case, it actually utilizes 283 kilojoules of energy. Now, if we will be adding these two values, okay, we will be having the same 393.5 kilojoules of energy. Okay, this is what Hess's law is about. And it is actually helpful in determining the enthalpy change of a reaction that is difficult to carry out experimentally. Let us now apply Hess's law of heat summation through example 8. Okay. For this example, we are actually required to determine the heat of reaction for this given reaction, that when carbon monoxide and nitric oxide reacts and forms carbon dioxide and molecular nitrogen, so how much energy is actually involved? Okay, now part of the given for this example is equation A and equation B. So for equation A, we have here the combination reaction of carbon monoxide and oxygen to form carbon dioxide, okay, involving this heat of energy or negative 283 kilojoules of energy. Okay. Equation B is the combination reaction of molecular nitrogen and oxygen to form 2 moles of nitric oxide, and this will be involving as heat of reaction for reaction B to be 180.6 kilojoules. Okay, so to solve this example, we must manipulate the given thermochemical equations A and B and their delta H values to get the target equation and its delta H. All substances except those in the target equation must cancel. Okay. So, as a start, we write the desired equation, okay, as given in the problem also, which is again nitric oxide and carbon monoxide reacting to form carbon dioxide and 1/2 mole of molecular nitrogen. Okay. Now, as stated, we are to manipulate the equation such that, okay, we will be able to follow the pattern, meaning we should be having from these two equations A and B that carbon monoxide should be on the left side as well as the nitric oxide. So for this case, equation A follows that carbon monoxide is on the left side, so we will leave it as is. However, for equation B, our nitric oxide is on the right side. So therefore, we will be reversing the equation. Another thing is that, okay, for the nitric oxide, our coefficient in the desired equation is only 1. But in the given equation, we have this to be 2. So therefore, we will also be dividing the whole equation by 2 in order to follow the coefficients of the desired equation. Okay. When we do that, you have to take note that we also will be having or putting in half the amount of energy that is involved in the creation of 1 mole of nitric oxide. Okay. So to show that, okay, we have this equation. So again, we manipulate the equations, we multiply the equation of B by 1/2 and reverse its sign. Okay, so we will be having this equation then, or this new equation for equation B, that 1 mole of nitric oxide is going to be equal to 1/2 mole of the molecular nitrogen and 1/2 mole of oxygen. And that 180.6 now becomes, will be half also, so having 90.3 and will become negative as we reverse the equation. Okay, and then what we do is we add the manipulated equations together, meaning again for A, it stays as is, and with B, we use the manipulated value. Okay, so in doing so, okay, this is going to be our equation A, and this is 1/2 of our equation B. And in that case, we are going to be adding these two equations such that, okay, the oxygen, the 1/2 mole of oxygen on the left side will be cancelled or will be eliminated by 1/2 mole of oxygen on the right side. And what will be left to us would only be the amount of carbon monoxide, okay, or the gaseous carbon monoxide on the left side of the equation, and the gaseous nitric oxide also on the left side of the equation. And then, on our right side of the equation, we will have, of course, 1 mole of CO2 and 1/2 mole of NO2, which is just the same as our desired equation. Okay, now the problem is actually, or this problem actually requires us to compute for that heat of the reaction for this given or desired equation. So how do we do that? Okay. What we will be doing is, from equations A and B, since we added them together, we will also be adding their respective heats of reaction. So therefore, the heat of reaction of A, which is negative 283 kilojoules per mole, no, will be added with that of 1/2 of the delta H of B, which is now negative 90.3 kilojoules per mole. And in effect, okay, we will be having as our answer negative 373 kilojoules per mole of the heat of reaction for this desired equation. Now we have standard enthalpy of formation and reaction. So the term standard is not new to us. Okay, remember that when we had gases in as our discussion in senior high, okay, we discussed to you the STP. So just take note that when we have standard states, we are actually setting specified conditions and concentrations to serve as our basis for our decisions as well as our generalizations for the quantities that we are trying to solve. So just take note that when we have gases, the standard state is at 1 atmosphere, and that when we have substances in a aqueous solution, the standard state is a 1 molar concentration. And once that we have pure substances, okay, either an element or a compound, okay, the standard state usually creates their most stable form, which is at 1 atmosphere and 298 Kelvin. So now we have the enthalpy of formation. Okay, enthalpy of formation is now gonna be noted as delta H also, but with the subscript of F, because this is different from your delta heat of reaction. So the enthalpy of formation, or delta HF, is the enthalpy of change associated with the formation of a compound from its constituent components. Okay, so our example that we have here as heat of formation is when methane is created from graphite and molecular hydrogen. Now, other than this enthalpy of formation, we also have what is referred to as the standard enthalpy of formation, and we will be noting this as delta HF naught. Okay, so here, remember that we are to set a condition. So the standard enthalpy of formation is actually the enthalpy change for the reaction that forms 1 mole of the compound, okay, from its elements, okay, with all substances in their standard states. Here is a table showing the standard enthalpies of formation of some inorganic substances at 25 degrees Celsius. Okay, it is worth noting here that based from the definition of the standard enthalpy of formation, our compounds such as silver chloride, aluminum oxide have values as compared to, let's say, our elements, which is not gonna be a part of our enthalpy of formation. Now we proceed with the standard enthalpy of reaction. Okay. Now for this one, it is worth noting that this enthalpy of reaction is gonna be different from the one that we had before, okay? Because this time we are gonna be having this naught symbol to differentiate the enthalpy of reaction to the standard enthalpy of reaction. Okay. Now how do we define the standard enthalpy of reaction? So sabi niya, the heat of reaction with all reactants and products in their standard states. Okay. It is also the net standard enthalpy of reaction that is equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So each standard heat of formation value is multiplied by the appropriate coefficient given by the thermochemical equation. Okay, so in order for us to determine that standard enthalpy of reaction, we are gonna be having this pattern. Okay. Now, what is involved here would be the standard enthalpies of formation. Okay. For the components that take part in our products, okay, and it will be multiplied with the corresponding number of moles for the product, and then we will be subtracting from here the sum of the standard enthalpy of formation of our reactants. Okay. Now, if let's say we are given an equation such that capitals A and B represents the substances as our reactants, and capital C and D acts as our product. Okay. Now, their lower cases represents their coefficient, okay, or respective coefficients. Now, to apply that in our definition here for the standard enthalpy of reaction, okay, what we will be doing is simply to follow this pattern. So, our products again are that of C and D. So, we will be determining the heat of formation of substance C and multiply that with the coefficient of substance C in the equation. And then, since this is a summation symbol that we have here, we are to add to that the heat of formation for substance D multiplied with the coefficient of substance D in our equation. Now, also, we do the same, only that we subtract the values coming from our reactants. And our reactants are again A and B. So, similarly, we obtain the heat of formation of substance A and multiply that with the coefficient of substance A from the equation. And then, add to this the standard heat of formation for substance B multiplied with the coefficient of substance B in our reaction. Getting the difference between the product or the heats of formation between the product and the reactant will give us the standard enthalpy of reaction. Let us now have an example that will require us to compute for the standard enthalpy of reaction. And this is example number 9. The problem says, nitric acid, whose worldwide annual production is nearly 10 billion kilograms, is used to make many products, including fertilizers, dyes, and explosives. The first step in the production process is the oxidation of ammonia, which is given by this chemical reaction. Now again, calculate the standard enthalpy of reaction from the standard enthalpy of formation values. Let us now proceed to the solution for the given problem identified as example number 9. Okay. Recall from the statement of the problem that we are given the reaction for the oxidation of ammonia to form nitric oxide and water. Okay. So, again, the problem requires us to calculate for the standard enthalpy of reaction from the standard enthalpy of formation values. Okay. Of course, since the basis would be the standard enthalpy of formation values, the first thing that we really need to do for this one is for us to obtain those standard of enthalpy values from our thermodynamic tables. So, checking on tables, you will be able to obtain this standard enthalpy of formation values for the gaseous form of our substances. For in the given reaction, all of them are in the gaseous form. Okay. Now, specifically for ammonia, nitric oxide, and water, okay, in their gaseous forms, these are their standard enthalpy of formation values. So for ammonia, that is negative 46.3 kilojoule per mole. For nitric oxide, that is 90.4 kilojoule per mole. Then for gaseous water, that is negative 241.8 kilojoules per mole. Now, oxygen, being only an element, okay, does not have any value for the standard enthalpy of formation. Because again, remember that thermodynamic property is applicable for the formation of 1 mole of a compound. Now, for us to solve this problem, okay, we will also be utilizing this pattern, okay, or this working equation in order for us to solve for the standard enthalpy of the reaction. But remember that this formula is simply getting the difference of the sum of the enthalpies of our products and subtract from that the sum of the standard enthalpy of formation of our reactants. Now, in utilizing this pattern or this formula, we have to consider the amounts of each of our products and the amounts of each of our reactants. That is stating or considering the number of moles that these substances have in our balanced equation. Okay, so showing that in mathematical form, we have this. So again, for the standard enthalpy of the reaction, okay, we work on the products first. And our product from the reaction is, of course, our nitric oxide, our 4 moles of nitric oxide, and 6 moles of water. Okay, so we will be substituting the coefficient for the nitric oxide and multiply that with the standard enthalpy of formation for nitric oxide. Then, again, we add the 6 moles of gaseous water and multiply that with the standard enthalpy of formation for gaseous water. Okay, so these two sums up the enthalpy of our products. Now, we subtract again the enthalpy of our reactants, from which we have again ammonia and oxygen. Now, from the equation again, there is 4 moles of ammonia, okay, and 5 moles of oxygen. Okay, now substituting our standard enthalpy of formation, okay, which are again this 46.3, 90.4, and negative 241.8. Okay, in this working equation that we have defined, okay, we will be having 4 times positive 90.4, and then add to that 6 moles times negative 241.8 kilojoule per mole. Then we subtract from that the 4 moles of ammonia multiplied with 46.3 kilojoule per mole, and of course that heat of formation coming from water or oxygen. Okay, in this case, we will be having as our final answer a negative 904 kilojoules as enthalpy of or standard enthalpy of reaction for this given reaction of the oxidation of ammonia. This PowerPoint presentation is developed based on these references. That ends our video presentation for the module on calorimetry.